Warm greetings of the day. Myself, Dr. Sanjaykumar Gowre, working as professor in the Department of Electronics and Communication Engineering, Madanapalle Institute of Technology and Science, deemed to be University, Madanapalle. First and foremost, I would like to convey my heartfelt thanks to MITS Madanapalle for giving me an opportunity to deliver a topic on photonic crystal fiber. So, I'll be covering this photonic crystal fiber topic under the following contents. So briefly, we will be introducing why this photonic crystal is required, what are the advantages, what are the disadvantages, what are the current fiber we are using. Then briefly, I'll go through what motivated us to take photonic crystal fiber as research topic, and then what are the challenges we will be having. Then we will be discussing about two important concepts in photonic crystal fiber. One is known as endlessly single mode fiber, the other one is dispersion. Then we will be discussing about what is photonic crystal, the three types of photonic crystals, one dimensional, two dimensional, and then three dimensional. Then applications of photonic crystals. In that specifically we'll be discussing about two applications, photonic crystal fiber and photonic bandgap fiber. Then disadvantages of this PCF and PBF. Then we'll be discussing about all glass photonic crystal fiber, some results and discussions followed by references. So before getting into the topic, let us look at this slide clearly. This is what is happening every minute of the day on the internet. So you can see many things are there: Facebook, WhatsApp, Instagram, Snapchat, Netflix, all these things. So if you look at this slide clearly, huge amount of data is being generated in 1 minute. And not only this data is being generated, we need to transmit this data from one place to another place. So there are various communication methods and models which are available for transmitting data from one place to another place. We may use optical fiber, or you can transmit wirelessly. You might be knowing that above 90% of the data is being transmitted from one place to another place using optical fiber. And our telephone data also more than 60% data is transmitted using optical fiber. So optical fiber plays a very important role in today's communication. As we all know that we have two types of fibers. Started our journey of fiber with multimode fiber, where the core area is around 50 micron. But the basic disadvantage of this multimode fiber is the dispersion. That means if you launch a pulse from one end, and if you're using multimode fiber, by the time it reaches the other end, the pulse will be broadened. So when we are transmitting many bits, so there will be overlapping of these pulses with respect to adjacent bits. So that is the basic disadvantage of multimode fiber. So the solution for that is go for single mode fiber, where the core area is around 8 to 12 micron, where only one mode is allowed to transmit from one place to another place. So in case of single mode fiber, the problem of dispersion what we had in multi-mode is negated. But still a single mode fiber will be also having some sort of dispersion known as what chromatic dispersion. But that dispersion is very less comparing to the dispersion what we will be getting in multi-mode fiber. So from last 2 to 3 decades, we are using this single mode fiber for the transmission of data from one place to another place. But this single mode fiber has got a distinct limitations. See, one limitation is what its core area is very less, 8 to 12 micron. Let us take an example that we want to design a communication link for say 100 kilometer using optical fiber or using single mode fiber. So if you look at the structure or architecture of the communication using fiber is what there will be a transmitter at one end, there will be a receiver at the other end, and then this transmitter and receiver we are connecting with the help of a fiber. So this fiber, whenever a pulse is transmitted, there will be two effects taking place. One is attenuation, that means the signal strength will be reduced. The other one is the dispersion. So for this attenuation, we have a solution is what? Use the repeaters or nothing but the amplifiers. So basically these repeaters will receive the signal, amplifies it, and then retransmit it. So basically these repeaters are nothing but the receiver and transmitter connected back to back with an amplifier in between. So if you look at the cost of repeaters, which consists of both transmitter and receiver, will be much more than the transmitter and then the receiver. So in a crux, when you design a optical communication link, uh, if you want to reduce the cost, then the number of repeaters should be less in the communication link. So if you want to reduce the number of repeaters in a link, let us assume that for 100 kilometer, we require 10 repeaters. So 10 repeaters means cost will be more. Can I reduce the cost by reducing the number of repeaters? Yes, you can reduce the number of repeaters. For that, you have to inject more amount of power into the single mode fiber, so that the number of repeaters count, say from 10, it may reduce to 8 or 7, depending on how much amount of energy we are injecting into the optical fiber. But problem in single mode fiber is moment you increase the amount of power that you will be injecting into fiber enters into non-linearity. That means in fiber we will be getting non-linear phenomena like cross-phase modulation, self-phase modulation, and then four-way mixing. So that is the problem. Then the solution for that is what? You can inject more amount of power, and then if you don't want to enter into non-linearity, you can increase the fiber core area. Moment you increase the fiber core area, so if it is more than 12 micron, fiber becomes multi-mode fiber. It is no more single mode fiber. So our hands are tied in case of single mode fiber, where the core area is limited only 12 micron, and then the amount of power injected without going into or without getting into nonlinearity is limited. So these are the limitations. The second limitation is about the dispersion. In case of single mode fiber, we have a chromatic dispersion. So at 1.3 micron, we have a zero dispersion. Below 1.3, we have a negative dispersion. Above 1.3, we have a positive dispersion. So by designing this core and cladding area, we can shift this zero dispersion from 1.3 to any value higher than 1.3. For example, if you want at 1.55, normally most of the optical communication will takes place at 1550 nanometer or 1.55 micron. So we can shift this zero dispersion from 1.3 to 1.55. But below 1.3, it is not possible to shift it. So these are the two fundamental limitations of single mode fiber. So these problems we can solve using photonic crystal fiber. So wherein we'll be getting a concept known as what endlessly single mode fiber. That means we can increase the fiber core area from 12 micron to 36 micron, nearly 3 times, but still we will be operating in a single mode regime. And then also this dispersion you can shift above 1.3 or below 1.3 also. So with this basic explanation, now we'll go into what is photonic crystal. So if you're looking at the figure, basically we have a three types of photonic crystals. One-dimensional photonic crystal, two-dimensional photonic crystal, and then three-dimensional photonic crystals, where the refractive index will be changing in either one direction, two direction, or three directions. So basically these photonic crystals are inhomogeneous metals with a periodic structure, where the dielectric properties will vary in space of the order of the light wavelength. So one dimensional is very basic, three dimensional is very complicated. Most of the time people are working in the two dimensional photonic crystals. So if you are looking at the figure, two figures, this photonic crystal you can design in either square lattice or hexagonal or triangular lattice. The first figure is basically is what dielectric rods in the air host. That means we have a rods with some refractive index, and then the host is air with a refractive index of 1. So if you're using this configuration, then we'll be getting a photonic band gap in TE mode. Whereas if you are looking at the second figure where we have air holes in the dielectric slab. So dielectric slab will be having a refractive index. If you are using silicon, that refractive index will be there, and air hole will be having refractive index of 1. So if you are using this configuration for photonic crystals, then we'll be getting photonic band gap in TM mode. So depending upon whether you want in TE mode or TM mode, we have to use any one of this configuration. Also, once you design this photonic crystal, two-dimension photonic crystals, you can create the defects in the photonic crystals also. So there are three types of defects you can create. One is known as what point defect. So basically, what is point defect is what you will be removing one rod, right? So if that one rod is not there, then it is known as what point defect, that can be used for cavity or as a ring resonator. If you remove the many these rods, right, in a line, then that is known as what line defect. Then that can be used as an waveguide. So from one side you can transmit signal, other side you can get it the output signal. So that acts as a waveguide. It has got many applications. You can use it for filters, bends and splitters, combiners, and then so on. Also we have a for mirror application, surface defect. So these are the applications of photonic crystals. You can see that there are many applications of photonic crystals, starting from fibers to waveguides to multiplexer, demultiplexers, filters, sensors, biosensors, logic gates, lasers. So this photonic crystal has got n number of applications. In this lecture, we will be discussing about photonic crystal fiber applications. So there are again two different types of fiber we can fabricate using photonic crystals. One is known as what photonic crystal fiber. The second one is known as what photonic band gap fiber. So if you're looking at the first figure, photonic crystal fiber, in center a roll is missing. So that acts as a core having a diameter of d, and then in the cladding part we have the air holes. So basically, as we all know that optical fiber works on a concept of total internal reflection. So we need a core and then we need a cladding. So in this case also the center part where aerole is missing, that acts as a core, and then in cladding we have a many air holes. Whereas in case of photonic band gap, the difference is what in center also we have a air hole, but you can see that the size of air hole at the center is more comparing to the air holes in the cladding. So these are the two types of fibers which we can design using photonic crystals. In case of normal fiber, we have only two parameters to play with, that is refractive index of core and then the refractive index of cladding. Whereas in case of this photonic crystal fiber and photonic band gap fiber, apart from these two, we have other parameters also. Right, we have a lattice pitch. Lattice pitch is nothing but the distance between two air holes, then air hole diameter, then ratio of air hole diameter to pitch, then the refractive index of glass. So we have a lot more flexibility in case of these photonic crystal fiber and photonic band gap fiber, so that we can design in such a way that even if we increase the core area up to 36 micron, the fiber will work in a single mode regime. The drawback of the previous photonic crystal fiber is what we have air holes in the cladding. So during fabrication, it is quite possible that there will be a deformation of air holes. That means the size of air holes will change. The air holes of adjacent area can merge, and then the air holes at the boundary will be deformed. So that is the disadvantage of normal photonic crystal fiber. So solution for that is all glass photonic crystal fiber, where instead of air holes we are using some material having a refractive index more than air, right? So in this structure, the problem of air hole deformation is taken care. Also along with the parameters, we have one more parameter, that doping concentration. So we have a lattice pitch, air hole diameter, refractive index of the glass, and then the doping concentration. All these parameters we can manipulate in such a way that we can design a fiber in such a way that it works in a single mode regime even if we increase the fiber core area. So let us see some results. So the first slide is basically for VPCF, that is V parameter, for a value of 3.144, that is V is equal to pi. So you can see that for a D by pitch value of 0.4 and 0.5, for any given wavelength, the fiber is operating in a single mode regime. But moment you increase the D by pitch from 0.5 to 0.6, 0.7, 0.8, for initial values, your fiber will be operating in a single mode regime. But as you increase the wavelength from 4 onwards, the fiber will get into multi-mode. It is no more single mode. So same thing we have simulated for a proposed all glass photonic crystal fiber also. So here also you can see that the fiber acts in a single mode rhythm for any given wavelength for a value of zero point 0.4, zero point 0.5 and 0.55 also. So you can see that in the proposed all glass photonic crystal fiber also it is showing the property of endlessly single mode um, phenomena, which is very important for designing a communication link with a less number of repeaters. Also we can see the dispersion results also. So in both the cases, that is photonic crystal fiber and then all glass photonic crystal fiber, you can see that zero dispersion is shifting to any value. In case of normal fiber, as we have discussed, it is not possible to shift zero dispersion below 1.3. But you can see in case of normal photonic crystal fiber and then all glass photonic crystal fiber, the zero dispersion is at 1.25 and then 1.3 and then 1.46, 1.51. That means we can design in such a way that whatever wavelength we want, at that wavelength we can have a zero dispersion. So this is the advantage of photonic crystal fiber. That is one is endlessly single mode property. Second one is a tunable dispersion, that is below 1.3. Tunable in the sense in normal fiber also it is tunable, but above 1.3 only, below 1.3 not possible. Whereas in case of photonic crystal fiber, below 1.3 also possible. So depending on the light source, depending on your application, we can select any wavelength and then we can design fiber in such a way that at that particular wavelength the dispersion is zero. So these are the few references which we have taken for preparation of this presentation. So if you have any queries, questions about this e-content and PPT, kindly we can leave your queries here. Thank you. Thank you one and all.